In the name of Allah Almighty, the Beneficent, the Merciful, welcome to PH101 Lab, and our today's experiment is experiment number 6, rotational dynamics. So, first of all, what is rotational dynamics? So, actually, dynamics is the branch of physics which deals with the motion of objects when a force is applied on that object. So dynamics is actually the branch of mechanics which deals with the motion of objects under the influence of force. Let's say I have a block of mass m and I applied certain force in this direction. So it will move as a result of this applied force and it will move with some acceleration a. So this is actually the part of mechanics, and if we are studying this force studying this system under the influence of force, so it will be the part of dynamics. Now the word rotational. So why rotational? Now if the system is rotating, let's say, if the system is not moving in a straight path or in a rectilinear path, it is rotating about a fixed point, then this system will be studied in rotational dynamics. It is the case of rotational dynamics. The study of rotational motion of the objects under the influence of force, we can say that it is the rotational dynamics. If the object is rotating about a fixed point, so definitely some torque will be there to rotate the object about a fixed point. So let's take an example of a disk. Let's say this is a disk, and this disk is, let's say, rotating about a fixed point. Just like we can take the example of CD player. So there we have a disk and the disk is rotating about a fixed point. So this disk is rotating, let's say, in this anti-clockwise direction, like this. So it's having some velocity, and if the disk is rotating, so we will call the velocity here to be the angular velocity. So in this case, if this is the center of mass of the disk, so the center of mass of the disk C dot m will be right in the middle of this disk. And what happens that this disk is rotating about this fixed axis. So we can say that the center of mass of this system is at rest. Is it? The center of mass of this system is at rest. Or we can say that the velocity of the center of mass of this system is equal to 0, because the disk is rotating about a fixed axis. So if the disk is rotating about a fixed axis, the center of mass or the axis passes through the center of mass. So the center of mass is at rest, but the disk is rotating due to some force, or we can say that a torque is responsible to move or to rotate this disk about this fixed point. So this is actually the case of rotational dynamics, and our experiment is about to study the angular velocity. So if we are talking about the angular velocity, definitely there will be some rotation involved. Now what is angular velocity? Let's say we take the example of this disk. Let's say this disk is rotating about a fixed point. This is, let's say, the axis of rotation. It is rotating in this direction, in the anti-clockwise direction. So let's say if the disk start at point A, let's say I mark a point A. I mark this disk with a dot, let's say. If the disk starts at point A and let's say it completes one revolution. So if it starts at A and it comes back to at this point and it comes back towards point A, so it will be one revolution. This will be one revolution. So it means that one revolution is equal to 2 pi radians. One revolution will be 2 pi radians. So what will be the angular velocity in this case? So angular velocity is a vector quantity omega. So omega is equal to theta by t, where theta is the angular displacement. So let's say if it moves from A and comes back towards A, so the angular displacement in this case, because if the disk is rotating, this point will, after some time, this point will be here, then it will be here, then it will come back towards A, and it will complete one revolution. So this theta will be actually equal to one revolution. And how much time is taken by the disk to complete one revolution? Let's say this is 1 second. Let's take the example of, for the sake of simplicity. So our angular velocity will be equal to 1 revolution per second, and 1 revolution is equal to 2 pi radians. One revolution is 2 pi. So this is, we can say that 2 pi by t. So this is actually the angular velocity. This is actually the radian per second. The units are the radian per second. So omega is equal to theta by t. This is the angular velocity. So if the disk is rotating, it starts at point A and it completes one revolution, then it will be 2 pi. If it completes 2 revolutions, this will be 4 pi. If it completes 3 revolutions, it will be 6 pi by t. And how much time is taken to complete these revolutions is t. So simply this is the vector quantity and this is the angular velocity. Now in the so we are discussing the prerequisites. Now one more thing is, we know that theta is equal to, for one revolution, theta is equal to 2 pi radian. Let's say if it completes 2 revolutions, then it will be 2 into 2 pi. It will give 4 pi radian. Then for 3 revolutions, it will be 6 pi radian. So for n number of revolutions, I can write this theta to be theta is equal to 2n pi radian. Or I can rewrite it to be 2 pi n radian. So we will be using these relations. That's why I am deriving this. We will be using this relation theta 2 pi. N is the number of revolutions. N is the number of revolutions, as you can see in the table as well. Number of revolutions. And 2 pi represents one revolution. So if n is 1, this is one revolution. If n is 2, this is 4 pi. So it's 2, it represents 2 revolutions. And similarly, theta is related as 2 pi n radian. So we know that we can use theta is equal to 2 pi n radian, and one relation is omega is equal to 2 pi by t. Now let's move towards our experiment. So the purpose of our experiment is to study the angular velocity. And the angular velocity, we are having some disks. In this case, we are having some disks. So the apparatus required for this experiment is the rotational dynamics unit. As you can see, we will need 3 disks actually. One is the aluminium disk and two disks will be the steel disks. Now we will need a stopwatch, the air compressor and the graph paper to graph the plot between the angular velocity and versus time at the end. So this is the apparatus, and the purpose of this experiment is very simple. We are studying actually the angular velocity of disks. So one is the aluminium disk and the other one is the steel disk. So both have the same radii. Keep in mind, both have same radii. Means the radius of the aluminium and the steel disks are same, but the masses are definitely different because the density is different. So as you can see that this is actually the rotational dynamics apparatus, and using this apparatus we will be finding the angular velocity. And how to do it? Let's understand this apparatus first. So this is actually our apparatus, rotational dynamics apparatus. There are 3 disks, as you can see. The bottom, we call this the base plate. So actually this is not a disk. You can say that it's a base plate and it's fixed. You cannot move it or rotate it simply. Inside, on this base plate, we have a spindle. So we have like a spindle and the disks are having hole in the middle. So we can keep the disk here inside this spindle. So we can keep the disks inside this spindle. Now the spindle contains, here we have a hole, and around the spindle we are having some holes. So these holes are actually for when the air from the air compressor goes into this tube, the air goes into this spindle and comes out of these holes, and this air is responsible to move these disks simply. So actually the spindle, this is actually the spindle right in the middle of these disks. So the spindle is, we call this the spindle. The spindle is having holes. Now there are 2 disks. One is the upper disk, the top one, and the bottom one is the lower disk. So keep in mind that the unit will always operate, this unit will always operate on 2 disks. So we will not be using single disk. We will be using 2 disks if we are using or if you are performing this experiment. It may be one steel disk and one aluminium disk, or it may be or it may be both steel discs. So the bottom disc is always the steel disc. Keep in mind, the bottom disc, we keep the bottom discs to be the steel disc always. So there are three discs actually. Two are the steel discs having the same radii, and one is the aluminium disc. So the first one is the upper disc. We call it the upper disc or the top disc. This one is the lower disc. These discs can rotate about this spindle. Now here we have a display screen. Digital display screens tells us about the counts per second. So what are actually the counts per second? So let me show you. So actually we are having this, I have this aluminium disc, and this one is the steel disc, as you can see. So on this disc you can see that there are black and white bars. If you can clearly see that there are black and white bars. So keep in mind, we have this, you can see the black dots. So these are actually the optical readers. So the optical readers actually reads these bars. So when there will be a light, there will be a light indicator. So these are the optical readers. So whenever the optical readers reads these black bars, so the light will turn on, and as it reads the white bar, the light will goes off. So keep in mind, whenever, because the disc is rotating and the optical reader, they are having white and black bars. So when the black bar, the optical reader reads the black bar, so the light will turn on, and as it reads the white bar, the the light will turn off. So this is actually the indicator. Now there are actually 200 bars on this disc. So keep in mind, we are having n is equal to 200 bars, you can say. So don't confuse this n and this n. We will be discussing it shortly. So I am representing this n to be 200 bars because there are 200 black strips or 200 black bars on this disc. So the function is very simple. First of all, we will turn on the air compressor. You have to keep in mind that these discs are actually rotating against each other. They can rotate against each other, or they can spin against each other. They can spin together, or they can spin independently. Keep in mind, they can spin independently. They can spin dependently means one disc can spin in one direction and the other disc can spin in the opposite direction. Similarly, there are certain holes, as you can see. I am calling these holes to be the valve pin storage positions. So the first two holes are actually the valve pin storage position, and the bottom one is the bottom disc valve. So actually this air tube passes under these holes. Now we have two pins, valve pins. As you can see, we have like we have a valve pin. Now here we have a switch. When you flip the switch to the upper mode, so it means that the first or the top disc is monitored by the optical reader, and the display screen will tell us about the counts per second. So actually it reads the count, the number of black bars as it passes across this optical reader. So if the black bar is passing and the optical reader is detecting the black bars, so counts per second means that the number of black bars detected by the optical reader per second. So it actually means counts per second because it is counting how many bars are moving in 1 second. So the display screen, when you switch the switch it to the upper mode. So before doing this experiment, we have to first turn on the air compressor. As the air moves inside this tube, so this air is actually providing the necessary force or the torque to rotate these discs. Before doing these things, first we will turn on the air compressor. And one more thing to keep in mind is because these discs are placed on one another. So if there will be dust, then there will be frictional forces involved, and the results will be the results will not be that much accurate. So you should not be rotating this disc against each other when the air compressor is not turned on. Because when the air compressor is in the off state, these discs are having enough friction between them. So if you will rotate these discs against each other, then definitely they will create some scratches against each other. So the scratches will be responsible to increase the friction of these discs, because when the air flows in, the friction between the disc reduces. On the top of the spindle, we can insert a pin, a valve pin. So there are actually two valve pins. These valve pins can either be inserted in the middle of the disc, or there are three holes, as you can see. One is the bottom disc valve and the other one is the valve pin positions. These two holes are for the valve pin positions, and this bottom disc valve is for the bottom disc position. So these holes having some functions. So if you will, there are actually two valve pins. So if this is our valve pin, let's say I am keeping one valve pin in the middle of this disc and one valve pin in these holes. If we have to study the rotational motion of the first disc, we will move this or flip this switch to the upper mode. So the optical reader will monitor the first disc, the top disc only. And if you flip it to the lower mode, the optical reader will monitor the bottom disc and will tell us the number of counts per second for the bottom disc. For if it is in the upper mode, this display screen will tell us the count per second, the number of black bars per second for the top disc. So this is very simple. Now, when the air compressor is turned on, actually the air required for this experiment is 9 psi. But because the pressure may vary depending on the type of the air compressor, so you should always be performing this experiment for constant pressure. So if you are not using the 9 psi value for the pressure, you can use any value, let's say, not too high pressure. Keep in mind, the pressure should not be too high to disturb the valve, to disturb these tubes. So you should always be performing this experiment for constant pressure and for moderate pressure, not too high and not too low, because the pressure should be always such that the discs are able to rotate freely. If the discs are not freely rotating, it means that when you turn on the air compressor and disturb the first disc slightly by your finger, and if it is rotating freely, it means that the air pressure is enough to provide the necessary force. Keep in mind. Now, the purpose of these are the valve disc holes, three holes. The first two are the valve pin storage positions, and the bottom is actually the bottom disc valve. This is the what are these holes for? These two discs can spin dependently and independently, and it depends on the position of this valve pin. So if this valve pin is in the, let's say these are the holes, the first two are the storage positions, and the bottom one is the bottom disc position. So if our valve pin, this is our valve pin, if this valve pin is in the one is inserted here, let's say I have inserted this valve pin in this hole, in the storage position. For the lower disc, we are having this middle one is for the lower disc and this upper one is for the top disc. So there are two storage positions for the first and for the second disc. So if I will be performing this experiment, I will have to keep the one of the valve pin in this storage position in the middle one. One valve pin will be in the middle of this hole right here, and the other pin will be in the middle of the spindle. Keep in mind. So there are actually two pins. The first pin will be in the storage position in the middle, and the other pin will be right in the spindle. So there are two pins, and so we will keep our second valve pin. So we will keep our second valve pin in the storage position, which is in the middle hole. So in between the holes. So if we keep this valve pin in the bottom, in the storage position in the middle, and one in the spindle, so what will happen? It means that the bottom disc will not rotate, and just the upper disc will rotate. This is for the case when one is in the spindle, one pin is in the spindle and one is in the storage position in the middle. So what will happen? It means that the bottom disc will not rotate and just the upper disc will rotate. So if we are studying for the aluminum disc, initially we are studying the angular velocity for the aluminum disc. We only want the upper disc to be in motion. So we will keep the valve pin to be in the middle. So it means that the bottom disc will not rotate and the upper disc will move freely. This is what these holes are for. This is the purpose of these holes and the valve pins. and the 12 pins. And the purpose of this middle pin is because the ear is going inside the spindle. It is necessary, it is important to keep one of the 12 pin in the disc. So when you will keep the pin in here, the ear will be uniformly distributed through these holes. And this ear will provide the force to these discs to rotate. If I move this spindle, I move this 12 pin to the bottom disc, which is not the requirement for our case, but let's say if I move this 12 pin to the bottom disc, what will happen after moving this to the bottom 12 position, to the bottom hole? If I rotate the upper disc, the lower disc will also start rotating in the same direction. Keep in mind. So the bottom position is for the case when you will disturb the first disc, it will disturb the second disc as well. And the middle, the storage position, is for the case that the lower disc will not rotate and the upper disc will move freely above this disc. So let me repeat this in order to understand the procedure and how to perform this experiment. So the first thing you have to do is to turn on air compressor. We have to turn on the air compressor. The pressure should be fixed and moderate. Keep in mind, not too high and not too low. The other thing, we will check the level of this. So you can use the bubble level to check the level of this unit, to check the level whether it is placed horizontally. So we have to keep it horizontal. Now the third thing is to turn on this supply. So if you want to turn this on, there will be a power supply. Turn the power supply on, the digital display will turn on simply. Now the next thing you have to do is to set up this equipment. And how to do it? Let's say I want to measure the angular velocity for the aluminum disc first. So what I have to do, I will first place the steel disc, then the aluminum disc, and then I will insert the 12 pin in the middle of the spindle, as you can see. And the next 12 pin will be in the storage position, the hole in the middle. You will also need a stopwatch, keep in mind. So you will need a stopwatch. Let me show you. So you will need a stopwatch. Now the third part is you will rotate this slightly by your finger. And keep in mind that this optical readers only reads between 100 and 700 Hertz. Any reading above or below this value will be not reliable. Keep in mind, any value above or below this value will not be reliable. You will not be rotating this too fast, because if you are doing it, it means that if it is crossing the value above 700, if the digital display screen measures the value to be, let's say, 800 Hertz or 800 counts per second, because this is the frequency, counts per second is the frequency. So you should always gently rotate the disc with your finger. So we will place a paper tape here on the top of the disc. So this is actually for measuring the number of revolutions of this disc. So how to do it? First, you will place a tape here on the top of the disc, right in front of the optical reader, parallel to the optical reader. Now you will gently rotate it by your finger. So rotate the upper disc. I will write it here. Number 4th point is rotate the upper disc slightly or gently by your finger. And keep in mind, the value should not cross 100, it should not be below 100, and it should not be above 700. So it should be between, let's say, 200 count per second, 300 count per second. So this is a reliable value. You can keep it for your measurement. You will rotate the disc with your finger and you will turn on the stopwatch simultaneously. Now, after 2 seconds, you will note the reading. So this will be actually, let's say it counts to be the 240 counts per second. This will be your RI. RI is the initial reading. It actually tells the value which is displayed on this digital display screen. Now keep in mind, after the initial reading, we are doing this experiment, let's say, for 10 revolutions. So this N is for, keep in mind, the value of n in this table is actually telling us the number of revolutions, and one n is this one. So this one n, this n is for the number of bars, or you can use the small n, not to confuse the capital N and the n. So the small n is actually the number of black bars on the disk, and the capital N is the number of revolutions. So you will turn on the stopwatch as you rotate the disk, you will turn on the stopwatch. So now definitely this tape is for to measure the number of revolutions. So let's say I am doing it for 10 revolutions. So you will count the number of revolutions. As it starts at this point and it comes back to this point, this will be 1 revolution, 2 revolution, 3 revolution, 4, 5, 6, 7, 8, 9 and 10. As it completes 10 revolutions, you will stop the stopwatch. And you will note the value, of time. Let's say this is 8.35 seconds, let's say. And as you turn off the stopwatch and as you stop the stopwatch, the digital display screen will again show you some value in counts per second. This will be actually your final reading. Let's say this will be let's say this is 200 counts per second. Let's say this is 200 counts per second. Now theta can be easily calculated. Theta is equal to, as we discussed, theta is equal to 2 pi n. We have derived this relation, 2 pi n radian. So theta is equal to 2 pi n is the number of revolution is 10 radian. So this means that theta is equal to 20 pi radian, or we can say that theta is equal to 20 pi is 62.83 radians. So theta will be 62.83 radian. 62.83 radian. So for each case, if the number of revolutions are 10, you will have to do it for all the trials. Now the value of R average. Now keep in mind, now this is very important. The angular velocity and one is the R average. R average is actually the average of the initial reading of the display screen and the final reading of the display screen. So if Ri plus Rf divided by 2 will give you the R average value. This is actually the frequency. It is in counts per second. Keep in mind, it is in counts per second. So the display screen will tell you the number of counts per second, the number of black bars per second. So R average, we can calculate it by taking the average of these two values. We will get the R average, sorry. So you will note that value down here. Now R average is actually equal to this relation. This omega is actually average angular velocity. So average angular velocity will be equal to theta in radians divided by, so we have calculated the theta, and divided by the time t, or the capital T, let's say. You can use the capital T if you want to, theta by t. So let's say our value is 62.83 radians divided by time. So the time is 8.35 seconds. So we will get the average value of the angular velocity in radian per second. You will note that value here in radian per second. Let's say it is 8.55 radian. Let's say, sorry, this one. This is 8.55 radian per second. And let's say this value was something, let's say this value was 235 counts per second. RF. RF is the average of the initial and the final reading of the display screen. Now the next thing is to calculate K. So keep in mind that actually K is a constant and K is actually telling us the radians per bar. K is actually telling us the radians per bar. How many radians per bar are there? So this is actually the K, and it is equal to, keep in mind, the value of K is equal to, it is related as K R average is equal to omega average. It is related to the average reading of the display screen and to the average angular velocity, like this. So from here, the value of K is equal to omega average divided by RAVG, R average. So what will happen? R average, omega average you have calculated, it is 8.55 radians per second, and R average is 235 counts per second. So what you will have to do, the units will cancel out, second will cancel out, and we will get the units will be, let's say the value of the omega average will be radian per second, and the value of the R average will be from that table. You will note it down. Let's say this is 235 counts per second, and let's say this is 8.53 radian per second. So second will cancels out, and we will get a value of K. For this experiment, for aluminium, you will get the value to be 0.033 for all the cases. So you will have to also calculate the value of K. When you will perform this experiment, you will get the same value with a little fluctuation in the reading. You will get the value to be 0.03 or 38 simply. So actually this value is radian. We are left with radian per count. Our count means 1 bar. So I can say that count is actually representing 1 bar. So I can say that radian per count, or I can say it is equal to radian per bar. So that's why I have written the value of K, and its units will be radian per bar. So you will note the value, and in the first stage you should get a value of 0.033. Similarly, you will get a value of let's say for the second case you get a value to be 0.032, 0.031. Let's say you are getting the value of K. Now again you will have to repeat this experiment. There we will have a gas valve, the air valve. Here we will have a air valve. So using the air valve, you can turn off and on the airflow. So if you will turn the valve off, the airflow inside will be stopped. The airflow inside will stop. And the display screen is updated every 2 seconds. So please, if you are performing this experiment, you should wait for at least 2 seconds, and then you will have to note the value here. So let's say for the second case, I am getting the value to be 235 counts per second. So let's say the first disc completes 10 revolutions in, let's say in 9.35 seconds. 9.35 seconds, and as I turn off you have to note these 3 values simultaneously, keep in mind. So you will be doing it very shortly and very accurately. So when you will stop the timer, you will note the value of the display screen. So let's say this gives you the value to be 193 counts per second. This gives a value of 193 counts per second. Theta will be constant because the number of revolutions is 10 and theta is equal to 2 pi n. So there is no value of t. So there is no time in this equation. So we will get a constant value for the theta. So if this is for 10 revolution, keep in mind, then we will get a constant value for the theta. Now the R average can be easily calculated, as we have discussed. This is actually the average of the final and the initial readings. So we will get a values after summing these two values and dividing by 2, we will get the R average. So let's say the R average is now 230. The values should decrease, keep in mind. Omega average can easily be calculated. Omega average can be calculated again by theta by t, as we have written the value of the omega average is theta by t. So theta, we have the value of theta from here, 62.83 radians, and we will divide this by time, 9.35 seconds. We will get the value of the omega average. Let's say this value is 8.31 radian per second. Again, we know the relation between the K, R average and the omega average. So from here we can easily calculate the value of K, and it will be, the units will cancel out. We have discussed it, and we will get the value of K to be again 0.03, or there may be a little error in this value. At the end we will also find the error in the value of K, and I will tell you how to do it. So this is actually for the second case, you will find the value of K. So we have calculated the angular velocity of the upper disk. Now do it for the third case, for the fourth, fifth, sixth. You will have to take several readings, and then you will get a series of values for the RF, RI, N, theta, R average, omega average, and K. So we will fill this table. Now for the second table, what you have to do, the experiment is the same, the procedure is the same. What you have to do, you will pull this spindle out, you will pull this valve pin out, and you will remove the upper disc. Now I told you that the lower disc is always the steel disc. So they are actually two steel discs. Now the lower disc will always be the steel disc. So when we will be demonstrating it practically, you will understand it better. But for the theory and calculations part, let's discuss it shortly. Now you will remove the aluminum disc and then you will keep the steel disc instead of the aluminum disc. So remove the aluminum disc and keep the steel disc. Now move this flip switch to the upper position. Now again the procedure is the same, but now the optical reader is monitoring the steel disc. In the first case, it was monitoring the aluminum disc. In the second case, because we have changed the disc, the upper disc, now it is monitoring the steel disc, and definitely the steel disc is more massive, so the results will vary. Definitely the results will vary, and you have to repeat these similar steps for the steel disc. So this was actually the rotational dynamics apparatus, and this was the way how to perform this experiment. Now one more thing is, you can also calculate the value of K. One value is to calculate it from the experiment. So we can do it from the experiment. And the other thing which is the requirement for this experiment, keep in mind, you should also calculate the value of K. You should also calculate the value of K. One is through this relation. One is through this relation. So one is through this relation. And one more thing is, K is actually equal to 2 pi by n. So if this is 2 pi divided by n is 200 bars. So this will be radian per bar, and you will get the value of K. This will be the theoretical value. Keep in mind. This is the experimental. You can say this is the experimental value of the K, and this is actually the theoretical. This is actually the theoretical, and then we will have to calculate the percentage difference. Now, if you calculate this value, this value will comes out to be 0.0314. So this is actually the theoretical value of K, and this was actually the experimental value of K. Now at the end you will have to calculate the percentage difference in the value of K. And how to do it? Now we know that we have a series of K values. So first you will calculate the average of the K. So you will sum all these values. Let's say there are 1, 2, 3, 4, 5, 6. Let's say there are 6 K values. So you will sum all these values and divide it by 6. You will get the K average. So you will have to calculate the K average from here, and this will be your experimental value, and one value can be the theoretical value. So the percentage difference in K is equal to the absolute of the theoretical value of K minus the average experimental value of K, which is K average. You will sum all the values of the K average. So you will sum all the values of the K and divide it by the number of values, and then divide it by the again theoretical value of K. So you will get the percentage difference, and it should be again less than 5% at least, or at least for this experiment, if it is less than 2%, it would be better. If it is less than 2%, it would be better for this case. Experiment seems to be very difficult in the theories and calculations part, but when I will be demonstrating it practically, you will come to know that it is very easy to do it practically. But when we will demonstrate it experimentally, you will definitely understand it very well. So this was all about our today's experiment. Now at the end, you will plot a graph, and the graph will be between the angular velocity. The graph will be between the angular velocity and the time. Angular velocity time graph. We will have to plot the angular velocity time graph. How to do it? On the y-axis, we are having the average velocity values. Average velocity in radian per second, definitely. And on this axis, by choosing the suitable scale, we are having the values of time. Let's say we have 6, 7 seconds, 8, 9, 10, 11, 12, 13. Here we have 4, 8, 12, 16. Now, the angular velocity value is decreasing. The average angular velocity is decreasing. So then you will have to plot a graph between the average velocity and the time. So as you can see that the value of the average velocity decreases with increasing time. The time is increasing. For the second case, we are having 9.35 seconds and the average velocity is now 8.31. So when you will get a series of values, you will come to know that the value of the average velocity decreases and the time of revolution increases. So if you are performing this experiment in the first go, keep in mind, if you are performing this experiment in the first go, you disturb the upper disk slightly by your finger and you have completed the first trial and then you have also completed the second trial, the third, the fourth, the fifth. So keep in mind, when you rotate this list slightly by your finger, so definitely it will move, initially it will move a little faster and then it will move a little slower. So its angular velocity will decrease, definitely. Its angular velocity will decrease because you have disturbed it with your finger. So the angular velocity of the disk will not be constant. For the first trial you have completed and the disk is continuously moving, keep in mind. So when you will do it for the second case, you will get the value of the average velocity decreases. For the third case, the value of the average velocity decreases, and definitely if the average velocity decreases, the time required to complete 10 revolution will increase, the time will increase. If the speed is of the angular velocity is decreasing, so more time is taken by this disk to complete 10 revolutions, so the time will increase. So if this is the situation, you will get a graph like this. So definitely it's not a constant angular acceleration. This is not a constant angular acceleration. This is a decreasing acceleration. This is actually a decreasing angular acceleration, and angular acceleration is omega by t. So the slope of this curve will give you if you will calculate the slope of this curve, you will come to know that the slope of the curve is actually the angular acceleration. Angular acceleration is the time rate of change of the angular velocity. So keep in mind, when you will do it for the first case, you will do it, so you will disturb the disk by your finger and you have noted these values down. Now do it quickly for the second case, for the third, for the fourth, for the fifth, without turning off the air valve. Do it for the second, third, fourth, fifth. Measure some values of k, fill this table. So you will come to know that when you will measure the third, the fourth, the fifth, the sixth value, the value of the average velocity decreases with time. And the time required to complete 10 revolutions increases, because if the velocity decreases, the time taken to complete 10 revolution will definitely increase, and you will get a graph like this. So you will have to plot a graph for the aluminium and for the steel disc as well. So this was all about our today's experiment, the rotational dynamics, and this was the rotational dynamics apparatus, and the purpose was to study the angular velocity of the aluminium disc and the steel disc. So this was all about our today's experiment, the rotational dynamics. We will practically demonstrate it in the second part. So thank you so very much for watching the lecture.